I'm delighted to be able to talk once again to the Iranian Society of Biology at its Congress this year, 22nd Congress 2022. And I'm going to talk about a problem that is of great interest to Iran, which is water. I'm going to talk about how the chemistry of life, biology, begins with water, and how it also forms the basis for our freedom, that is, our free will as living organisms. Now, first of all, the question is, why is that question, the question of do we have freedom, do we organisms, living organisms, have freedom, why is that so controversial? And I think that is because it may seem obvious that since organisms are made of and evolved from chemical compounds and processes, they cannot escape being chemically determined, because we don't expect purely chemical processes to be capable of making responsible decisions. That's one of the reasons why we are cautious about driverless cars on our streets, because the ethical and legal problems don't depend on the science, but on attributing legal responsibility, whether to owners of cars or to the car makers. In both cases, though, ultimate responsibility is attributed to humans, organisms, not to the machine. Now, what I'm going to do is to show you that precisely because of the kinds of chemistry that enables organisms to exist, they cannot be determinate machines. And that conclusion is the exact opposite to the central dogma of molecular biology formulated by Francis Crick in 1956. That dogma says we are formed by our genes. It's the idea of a very famous book, The Selfish Gene, that from the genome alone we could predict the organism. I will show it's just the other way round. Organisms themselves control their genomes. I showed this in my book, Dance to the Tune of Life, published just 6 years ago, and I'm going to explain why. So what is our chemistry? What exactly are we made of? Well, life is largely made of the most common elements in the universe: hydrogen, carbon, oxygen, and nitrogen. And they're combined in unimaginably large numbers of possible ways. DNAs, RNAs, and proteins are all long polymers made of those elements, threads of sequences of either nucleotides or amino acids. Human DNA, yours and mine, is around 3 billion such nucleotides in length. And genomes are unique to each individual because there wouldn't be enough stuff in the whole universe for every possible sequence of 3 billion genomes to exist. The mathematics of that can be found in my little book, The Music of Life, published in 2006. There could actually be 10 to the 70,000 different combinations of interactions from our genes. But there are only about 10 to the 80 atoms in the whole of the visible universe. Each of us, therefore, is unique and a highly improbable, specific organism with its own unique DNA. Now, each of us might be just a highly unique and improbable machine. But we might still be machines determined by our genes and proteins. So why am I arguing that can't be the case? Well, it comes back to water again. Because water is a very unusual form of chemical. First of all, the range over which it is liquid. Those two elements, hydrogen and oxygen, combined to make the smallest and the great majority of all the molecules in our body, that is, water molecules. They depend on the fact that water is liquid at a range of temperatures way above the maximum temperatures at which both of its atoms could be liquid. Oxygen vaporizes at minus 90 centigrade, hydrogen at minus 253 centigrade. So the bonding of hydrogen and oxygen is responsible for an enormous increase in the temperature of condensation. That's why water is liquid at the kinds of temperatures at which life can occur. The second reason why it's a very unusual chemical is it's a good solvent for most chemical compounds. It's flexible, and nearly all the molecules can be dissolved in it. But the ones that can't are very important to my talk. They are the fats. Fats cannot be dissolved in water. They can exist in a water suspension. Every good cook knows how to make a sauce by whisking up an oil-water suspension, which we call a sauce. But the fats in us are not like suspensions. They're more like soap bubbles than fat globules. And those bubbles form the vast structures of membranes in our cells, tissues, and organs. And those membranes are where nearly all the control processes in our body are located. It's those proteins in our lipid membranes that are important. So, the book of life, the genome. How did the genome become described as the book of life, creating us body and mind, as Richard Dawkins says in his Selfish Gene? If that were so, the conditional logic of life would have to be found in the genome. But if, as a computer programmer, like me for example, you look for where all of those conditional logic statements are, the if, then, else control routines, if you look for where those are in the genome, you will not find them in the genome. There are switches in genomes, places where genes are switched on or off, but those switches are controlled by other physiological processes. So there is no book of life in the genome. So where are life's control routines? Well, they're in those fatty membranes and their protein channels. Those are our conditional on-off switches. Those are the processes that are sensitive to electrical and chemical processes in the world around us and within us. And without those membrane processes, there could not be choice between various behavioral options. Choice is an essential element in any theory of variable free action. Also, interestingly, all our nerve cells have these controllable on-off switches. So do all the other cells in our bodies. So when did intelligent life on Earth begin? Well, I suggest it began with membranes. It's when the first cells emerged with their membranes during the evolutionary process, and that is when intelligence became possible in living systems. The intelligence of life, therefore, lies in our membranes, and the processes they enable, not in our genomes. Moreover, there are no genes for the fats and lipids in our bodies. All the membranous structures are inherited independently of DNA. Remember, the decision-making processes cannot be in the genome. Now I come to two other major properties of water that are very important in my story. Another very unusual chemical fact is that the frozen form of water, ice, floats. And that's because water freezes in a very unusual way. Ice is lighter than liquid water, so it floats on lakes and seas. All other possible solvents do the reverse. Their frozen forms sink. But since ice floats, large expanses of water in lakes and seas remain open to living systems. They continue to flourish even between and beneath the ice. The ice even acts as a barrier to heat loss because ice is actually a good insulator. That's why we think that life on Earth survived the long periods when the Earth was frozen over like an ice ball. Life may therefore exist elsewhere in the solar system, on planets or moons that are completely iced over. Now I come to a fourth very important property of water, and the one that is really relevant to the question of why organisms have free action. It's Brownian motion. It was first observed in 1827 by a scientist called Robert Brown, which is why we call it Brownian motion. He ground up pollen grains to form even smaller particles, pollen dust if you like. He then sprinkled that fine dust onto the surface of water under a microscope, and he saw that all the particles were continually jiggling around in a random way. They were hardly ever stationary. Nearly a century later, in 1905, Albert Einstein showed that the movements of the dust particles were due to their continual buffeting by the incessant movement of the water molecules. So the jiggling of the dust particles was due to the random movements of the water molecules. Now I want to ask an interesting question. Could silicon or metals in your computers do the same? Because this would explain why liquid is important. You see, the atoms in silicon and metal structures may be vibrating, but they are not moving around in the way they do in water-based systems. All the molecules in water-based systems, dissolved or suspended in water, all will show Brownian motion. And this is a fundamental difference between living organisms and solid-state computers. Now we come to another important fact. Our genetic material, DNA, it cannot be exempt from Brownian motion because it's being continually buffeted by water. The DNA threads must therefore also experience that random motion. They exist in a water-based environment. They are threads that are suspended in the water-based environment. And what happens sometimes is that there is what we call DNA breakage. Now, my opponents in evolutionary biology, the neo-Darwinists as they call themselves, they also say, yes, there is chance, there is stochasticity, but I don't think they understand it. Importantly, they will say it's blind chance. Because during our lifetimes, none of those blind chance events can be used by us or other organisms in any functional way. As a consequence, they say, there can be no physiological basis for free choice based on molecular level stochasticity. That's why neo-Darwinists like Jerry Coyne, illustrated here, conclude that free choice is just a magnificent illusion. He writes, actually, and I'll quote from his book, "The illusion of agency is so powerful that even strong incompatibilists like myself will always act as if we had choices, even though we know we don't. We have no such choice in the matter," he says, "but we can at least ponder why evolution might have bequeathed us, given us such a powerful illusion." Incidentally, note the striking contradiction. Who is this we that can ponder why? Because from Jerry Coyne's viewpoint, why are we even capable of doing that and to choose either to agree or disagree with his statement? But I will leave that contradiction to one side, because I want first to explain why this is such a common idea taken by neo-Darwinists. Because even though neo-Darwinism makes blind chance a cornerstone of its case, it denies that that applies to DNA replication. On the contrary, DNA is claimed to be a highly accurate self-replicator, only occasionally suffering chance variations. The claim is that it does so by replicating like a crystal. So does DNA replicate like a crystal? Well, that would be possible, and indeed it happens. But that process alone produces many, many errors. Because replicating like a crystal can only occur if the individual components, the nucleotides C, G, A, and T, can automatically insert themselves into the correct position in the DNA sequence. Now, to some extent, that does happen. C likes to combine with a G. T likes to combine with an A. This is straightforward chemistry, and we can call it crystal-like if we wish. But stochasticity ensures that every so often the wrong nucleotide gets inserted. And we actually know the frequency with which that happens. It is one mistake in roughly 10,000 nucleotides. Now that may not sound very much. If you or I wrote an article of 10,000 words, it would correspond to just one typing mistake in 10,000 words. But our genomes are 3 billion nucleotides long. The error rate of natural crystal-like formation would generate hundreds of thousands of errors. No organism would survive that degree of damage to its DNA. Replicating like a crystal is therefore totally inadequate to the task. So what happens? What happens is simply marvelous. Organisms ensure that normally that degree of DNA damage does not occur, and how they do it is ingenious, and only living systems can do it. Each and every one of those errors is corrected by the living cell itself, employing many DNA cutting and splicing proteins to do the job. And the outcome is so accurate that it can reduce a natural crystal-like error rate of 1 in 10 to the 4 to just 1 in 10 to the 10. That is a 1 million-fold change and only a living cell, not the DNA alone, can achieve this. To use Richard Dawkins' language, the replicator DNA is not therefore separate from its vehicle, the living organism, and that fact alone destroys the central assumption of selfish gene theory. Not only does the living cell perform this miracle, if you want to call it that, of preservation of its DNA sequence, it can choose to regulate the error-correcting process. If the error-correcting process is down-regulated, the result can be many, many new DNA sequences from which the living organism can choose. It can even choose which parts of the genome to protect and which to change. This was shown many, many years ago by a very famous woman geneticist, Barbara McClintock. Her experiments in the 1950s on the plant maize showed that this ability to change a genome when the plant or the organism is under stress is universal. Under stress, all organisms can, as it were, spin the wheel of chance in the hope of finding a solution to the problem of survival. Bacteria can also do it. That was shown by the biochemist James Shapiro. In fact, all organisms can do it, and they use this ability to regulate the degree of correction of the genome to generate new sequences when they need to do so. I call these processes the harnessing, the control of stochasticity, the control of chance. It's the control of chance enabling organisms to be creative. The article was published by the journal Interface Focus in 2017, and it has consequences in evolutionary biology and in the philosophy of choice in organisms. In a series of articles that I've published in the last 5 years, they can be downloaded from the website, as my slide shows, that gives openness and flexibility to living organisms. Because it is dependent on natural occurring stochasticity, it is very different from the openness and flexibility of solid-state computers made of silicon and metal, because we, the living organisms, are the natural miners of chance that enable us to be so creative in what we do. Enable us to be creative? Could that also happen in our nervous systems? You bet it does. Nerve cells are densely packed with ion channels in their membranes, and those channels are also continuously jiggling around in a stochastic dance. And nervous systems are almost designed to be harnessing chance. Just as the immune system can distinguish between the forms of DNA variation that enable it to latch on to a new virus or a new bacterium, so our nervous systems can latch on to the neural mechanisms that satisfy the criterion of social choice. This is not a new idea, incidentally. It was originally formulated by Gerald Edelman, who won a Nobel Prize in 1972 for his discovery of the structure of the immune system's immunoglobulin proteins. He went on to suggest the same harnessing of chance could be operating in the nervous system. He even called it neural Darwinism in a book that he published many years ago. So, I've pursued this question together with my brother, the zoologist and philosopher Raymond Noble, to ask the question, does that enable values to influence physiology? Choice of what we should do. And where in those articles I argue that conscious organisms have the ability to match up their behavioral routines with the constraints of social interactions, including, for example, the concepts of fairness and the many other values by which we all live our lives. If that is so, then we have a process by which natural stochasticity, chance, can be harnessed, that is, used to enable us to act with what philosophers call the only free will worth having. But can conscious choice influence our biochemistry and control the genome in that way? Now I come to a very interesting study that physiologists have done over many years, looking at identical twins. Identical twins have nearly identical genomes. There are small differences, but they're very slight. Now imagine that one of them is brought up in an environment that leads to him choosing to train as an athlete and the other does not. Not surprisingly, as shown in the photo here, the body builds are completely different. And in an extensive study of such cases of identical twins, physiologists have been able to identify the control RNAs in the athletic ones that enable their muscle proteins to grow so much. So, the decision to train as an athlete, and provided that decision is implemented in practice, leads to precisely those changes at a molecular level that enable the athlete to succeed. Now, what is impressive about this study is that it identifies the small RNA molecules that control the genome. And in fact, this is happening all the time. Our decisions to do whatever we do are inevitably controlling our genomes, because similar physiological processes must be involved. There are armies of small RNAs, control RNAs, waiting to do just this. Now, is this what we call free will? What I've shown is that the harnessing, the use of stochasticity or chance clearly enables a form of creativity and behavior that allows social constraints and the ideas of value and judgment that go with them to influence the physiology of our bodies. But why should we call this free will? Doesn't it mean that, after all, we're still determined, but just by social interaction processes rather than by physical processes? Well, yes, that's true in a sense. But what surely would disturb us as a challenge to our ability to choose would be a demonstration that they were always impelled to do what we do by purely physical processes. My genes made me do it is even the title of a book. So, being physically compelled and socially influenced are very different forms of determination. Being influenced, even feeling compelled by the social influences of shared values and judgments, surely does not worry us in the same way. We can even observe the same processes in other species. Packs of dogs, illustrated in my image here, and groups of monkeys have both been shown in careful studies to be capable of discriminating against the members of the pack who are not cooperating. These distinctions, therefore, between the physical and the social influences are surely the basis for what many philosophers refer to when they talk about the kind of free will worth having. You see, as the person Denis Noble, I'm not worried by the fact that my upbringing and my social interactions greatly influence my values and therefore my actions. Why ever should I wish it to be otherwise? So social freedom is the form of free will worth having. Furthermore, influence by social factors does not imply compulsion. Social factors and the reasons we may give for our actions are what philosophers call defeasible, meaning that in retrospect we can change the reasons we may give for what we do. Legal processes in our law courts illustrate that process all the time. The concept of defeasibility was developed as a legal concept as well as having a philosophical basis. Now, clarifying what kinds of free will are worth having is indeed a philosophical question. But what I hope I have done is to outline a way in which physiological processes dependent upon the stochastic properties of water, and in turn therefore the stochastic properties of all the molecules that are in and dissolved in or suspended in water, can exist that enable that kind of free will to occur. Indeed, I would go further. Given what we know of the chemistry of life, of its dependence upon these interesting properties of water, and the ability for water to give us the variability that we need to make choices, given all of that, that kind of free action must surely be true. Now I want to come to a final plea, back to the question of water, because I want to finish this talk by returning to the unusual and amazing properties of water. And you people in Iran will know only too well the importance of water. You have sessions at this Congress on the importance of water preservation. And you might think this is a concern only in the traditional arid areas of the world. Well, I tell you, it's much more serious than that. My own country, England, illustrated in this image, is also suffering a drought this year. The whole of the eastern part of my country is at the moment in a disastrous drought state. You can see the ground is brown, it's not green. So even in England's green and pleasant land, water is now a scarcity. The countryside is no longer green. It is therefore urgent that young people everywhere in the world should plead with their rulers to save the world, because life, as we've seen, cannot exist without water. So I want to finish this talk with a wake-up call to the world everywhere, not only in Iran and my country, England, but everywhere in the world. Because the challenge is at a scale which human society has never faced before. The climate change problem is a problem for a new generation to create a world fit for the challenges of the 21st century. They, that upcoming generation, there will be plenty of looming signposts to warn them what went wrong. The fires, the droughts, and the other problems. So their generation will be the one that has to take responsibility for the way in which the Earth's ecosystems need rescuing, even for our own species, we humans, to survive. Theirs will be a generation that can try to recover from the damage to society that results from reductionist models of physiology and evolution that have metaphorically shaped ideas and models in fields as diverse as economics, sociology, philosophy, ethics, politics. The list goes on, because no aspect of today's society can have escaped dogmas like we are born selfish. They, genes, has created us body and mind. It's in his DNA, and all the myriad of other tropes have related types that we now use almost without thinking. Those future generations will also need to rewrite the textbooks, not only because they see the virtue of "let us therefore teach our children," to quote Richard Dawkins, but also because their politicians, economists, sociologists and philosophers will also need to find new strategies in collaboration with biologists and ecologists who can lead them out of the gene-centric impasse. It is arguably a challenge the scale of which human society has never faced before, because the very future of life of humans on this planet is at stake. So I wish them all well. The chemistry of life begins and ends with water. So thank you very much for your attention at this Congress in Iran. You can download all the articles I've referred to free of charge from my website www.denisnoble.com. Thank you very much, and thank you for asking me yet again to talk to the Iranian Congress of Biology.